Hi, this is Sarthak and this is a demo video for lab number 8 for the course EE533 under Professor Young Cho. The purpose of this lab was to create a convertible FIFO, which was supposed to work as a dual port memory, a DMEM for our 5-stage pipeline, and also as a FIFO for our net FPGA. The second purpose of this lab was to figure out how to get the FIFO interface with our net FPGA, write one packet into it, and see if we can generate a signal that lets my processor know that the packet is now ready for processing. Uh, to go into this lab, I'll first start explaining the diagram, the one we referenced. In the previous lab with the mini IDS system, we had a small FIFO, which was sending data to a drop FIFO, and then if the packets matched, we were dropping those packets using a 7-byte pattern matcher. In this case, we're going to be using a controller module that we created to interface between the small FIFO and the memory, the convertible FIFO that we are going to use. The in underscore write comes from the net FPGA, in underscore control also comes from the net FPGA, and so does in underscore data. We get out underscore ready signal from a downstream module that suggests that that particular downstream module is ready to receive data from our module. Essentially, our small FIFO will send out data into our controller, which will then parse the entire packet, take care of the tail and the head pointers, and then send out the data to our FIFO depending on what mode we are using. For example, if we are using the FIFO mode, we will require the read enable to be switched on for the small FIFO and the write enable to be switched on for the convertible FIFO at the same time. This is because the small FIFO will actually need to write to our FIFO, but instead it will go to the controller, which will then parse the data and then in chunks send the data out towards my FIFO, towards my convertible FIFO. If the FIFO is to be used in the CPU mode, our 5-stage pipeline kicks in, and that will start sending signals to the FIFO to write data into it or read from it. For example, in this stage, on the top right corner, you see the MEM stage of the 5-stage pipeline, which essentially connects to our DMEM, which is this FIFO on the screen. If the CPU mode is on, we see the read enable, the write enable, the address, the data, and then outputs that go back to our executions, go back to the write back stage of our pipeline. If we were using the FIFO mode, then essentially the data will be carried out from a separate port into our downstream module, which was ready to receive data as per out underscore ready. Next, I'll show you exactly what the signals are. We'll say that we'll take the reference of this crypto underscore Nick program. We see that this out underscore ready is essentially an input to crypto underscore Nick, and out underscore in OQ underscore in underscore ready is the signal that comes from the downstream module, which is output queues. So the output queues essentially sends the ready signal to my crypto module, which then tells, okay, I'm ready to receive data, you can now send. Crypto module, on the other hand, sends out the data along with the control signals, along with a write signal that tells my output queues module that the data is valid on the control bus. Referencing this image again, we see that the packet has to be in a particular format to be parsed. And that particular packet is essentially assembled in this way, where the first 8 bits of the data are the control bits, and the next 64 bits are the data values. If our control bits are not 0 initially, we see that it's definitely a header. Then immediately once the control bits are recognized to be 0, we see that our data packets and the actual payload has started. And finally, once the control bits become non-zero again, we'll see that our data packets again this is the last byte that we need to store. Now finally, I'm going to show my code and my test bench. As you see on the screen, we'll see that first we'll begin with the switch signal. This signal essentially oscillates between, makes my FIFO oscillate between the CPU mode and the memory DMEM mode. If the switch is 1, we'll say that we have entered the FIFO mode. The net FPGA can write into my FIFO. And apart from that, if the switch is 0, then we'll have entered the memory stage of the pipeline. Essentially, if my small FIFO, which is going to transfer my data to my FIFO, my actual to be written FIFO is 0, it means that there is some data to be transferred. We'll essentially set the signals based on that. We'll say that we are going to write into the FIFO and we are going to read from the small FIFO. This particular FSM essentially parses through the packet in the format that I showed you just a few seconds back, and says that if my control value is non-zero, we know that we are going to store the headers. Finally, we are going to start parsing the headers, go through all those. Then once the payload starts, once the control value becomes 0 again, we'll see that our actual payload starts here. And every single clock we'll be sending the data out from our control module into our FIFO. Finally, the last packet of the last packet of the entire packet, the entire frame, is recognized and stored into our FIFO again. Essentially, if the switch is off, we'll see that this proc write enable I is the signal that we'll get from our 5-stage pipeline. And if that write enable is on, we'll get the address from the arithmetic logical unit. We'll write the data into the memory that will also be given by the ALU, and then followed by the write enable signal for the memory, all at the same time. Again, same for the write. For the read, if we have a read signal, we'll need the address to read and the write enable signal. Finally, if none of the read and the writes are true, we'll say that we neither want to write nor want to read from our FIFO, and the memory just simply stores previous values. These tail pointers, I forgot to mention the tail pointers in the above as well. So the tail pointers are going to essentially, as we are writing chunks of the packets into the FIFO, we'll keep incrementing our tail pointers every single cycle till the write enable signal is off. Similarly, we still need to increment our tail pointer as our memory gets written into by the 5-stage pipeline, and we'll see that if the write enable signal is on and my FIFO is not full, we'll keep incrementing, we keep writing the data into the FIFO and keep incrementing the tail pointer. Otherwise, we keep latching that value. Finally, we needed to generate full and empty signals for our FIFO, which essentially meant that for the purposes of this lab, we were supposed to generate a full signal as we enter the end packet stage, which means that once we have buffered one single network packet, we'll say that our FIFO is full, and essentially these signals will generate the empty and check whether the packet is actually read or not. Finally, there was supposed to be a signal that we need to send to our 5-stage pipeline, suggesting that the entire packet has been buffered and it can start processing or reading that data, which is essentially this ready for CPU processing signal. I'm going to show my simulation here. Essentially, if my switch is off, we'll say that we have entered the CPU stage of the DMEM stage of the code, and this is the data that needs to be written from the FIFO and the ALU result and the address and the memory. In the next cycle, we'll essentially have written those particular addresses and the packets into our FIFO. Our tail pointer has been incremented, and we do nothing else since the switch is again 0. At a later point in time, we see that the switch has become 1, which means now we are going to act. This memory is going to act as a normal FIFO, get data from the net FPGA, and send data out towards my downstream modules. And in the next cycle, we'll see that as my input data comes in with the control signals, I am writing this data outwards from the control module into my FIFO. So essentially, all these 5 packets get written and my tail pointer gets incremented correctly. So since this was the second packet in the FIFO, we'll say that it's 002, 3, 4, 5, and then finally 6, which essentially buffers the last packet along with its control signals. At the end of the simulation, we have also incremented the header addresses because this is where my ready signal comes in, and my downstream module is ready to receive the packets from our current module, and so our FIFO head needs to increment as the packet chunks are being written out of the FIFO. Essentially, all these 5 packets are going into the downstream module, but not the 6th one, since that was the packet that was for the memory. As we increment the read procedure, the processor read enable, we'll see that the 6th packet also gets read. We are still working on the interfacing this module with the NetFPGA, and while we are able to get the addresses up and running, we are still yet to see the data on our NetFPGA. We'll be submitting this code along with the simulation wave files onto our GitHub. Thanks for watching.